Okay, 1992 AB4. Consider the curve defined by the equation y plus cosine y equals x plus 1 for the given interval. Find dy dx in terms of y. Well, notice this equation, y plus cosine y. Notice that it's not solved for y, and it'd be pretty hard to solve for y. I think for us, pretty impossible, because you can't factor a y out because this is not multiplication, it's cosine of y, so that y is inside of that cosine. The only way to get rid of that cosine is inverse cosine. So I can't solve for y, so I'm going to have to use implicit differentiation. So derivative of y with respect to x would be dy dx plus cosine y. I need to do that implicitly. So the derivative of cosine is negative sine y times dy dx, the derivative of y. And that technically it's a 1 dy dx, but I don't need the 1. On the other side, the derivative of x is just going to be 1. Now you want to collect all your dy dx stuff to one side, which it's already done, so I'm going to factor out dy dx. Really nice. Oops. I guess you could go ahead and divide at the same time, but I'm not going to. 1 minus sine y equals 1. And then finally, dy dx, if you divide, would be equal to 1 divided by 1 minus sine y. So there's my derivative. There's part A. Part B, write an equation for each vertical tangent to the curve. Well, if I want a vertical tangent, I want a vertical line. So in other words, I want to know when is the slope of the tangent line. If it's going to be a vertical tangent line, I want to know when the slope is undefined. If the slope is 0, it's a horizontal tangent line, so I want to know when the slope of the tangent line is undefined. So the only way that's going to happen is when the denominator of the fraction equals 0. When you get 0 in the denominator, you get 1 divided by 0, and that's an undefined slope. So I want to know when it's undefined. So I'm going to set 1 minus sine y equal to 0. Now, remember they said this was from 0 to 2 pi, so we only have solutions from 0 to 2 pi. So I'm going to subtract 1, so we're going to get sine y. Actually, I'm going to add sine y equal to 1. So I added sine y to both sides, and I just flip-flopped the sides. Now I'm going to take the inverse sine of both sides. Remember, inverse sine cancels the sine. Okay? So inverse sine cancels the sine. I'm left with y equals inverse sine of 1. Think about the unit circle from 0 to 2 pi. When is sine going to be equal to 1? Well, when y is equal to 1. And I can only think of one place. That'd be pi over 2. So that's going to be your solution. That's going to be where, so at pi over 2, so with that said, you need to find the way that, the reason this is a trick question is it wants the equation for the vertical tangent line. So I know that happens when y equals pi over 2. So here's the tricky part, because most of you think, well, this is a really easy problem. The reason it's a free response is if I want to write an equation for the vertical tangent line, I know what's going to make this slope undefined, y equal pi over 2, but a vertical line's x equals. So what I need to do is I need to plug this y value back into the original equation to find the x value. Okay? So I got to plug that y value back into the original equation. So I have y, remember it was y plus cosine y is equal to x plus 1. So we're going to have pi over 2 plus cosine of pi over 2 is equal to x plus 1. Now cosine of pi over 2 is just 0. So we're going to have pi over 2 is equal to x plus 1. So x is going to equal pi over 2 minus 1, and this would be your vertical line. That would be the vertical line equation. So I know that the vertical tangent is going to be x equals pi over 2 minus 1, whatever that is. Okay? So now the last thing asked to do is to find the second derivative. So I really need another page for this. So I'm going to take it to another slide. And remember, So remember, the derivative was this, and the original function was this. So if I want to find the second derivative, d squared y over dx squared, probably what I'd do to avoid quotient rule is I'd probably move this to the top, like this, to the -1 power. Also, I don't know if I need this right here. So I could, I guess, erase that. No, I'll just leave it there. Just know that that was the original equation. So this was the way I'd write it so I don't have to use quotient rule. So if I'm going to do this with chain rule instead, it's going to be -1 times 1 minus sine y to the -2, then times the derivative of the inside, which derivative of 1 is 0. And then we've got a negative in front of the sine, but derivative of sine is cosine y, that's a parentheses, times dy dx. So I've got a -1 times this negative over here is actually going to be, this negative times this negative is going to be a +1 times cosine y dy dx over 1 minus sine y squared. Now remember, you have to double back and look for two substitutions in particular. The first substitution is a dy dx substitution. So I'm going to plug in that dy dx. So I'm going to have cosine y times the derivative, which is 1 over 1 minus sine y, all over 1 minus sine y cubed, or sine y squared. Now, I don't want to leave that fraction on top, so I'm going to multiply by 1 minus sine y just to get rid of it. And then what I do at the top, I have to do the bottom. That's why I said cubed a second ago. I'm getting ahead of myself. When I multiply here, since this is all multiplied together, this is just going to cancel. I'm going to be left with cosine y over here. We're going to get cubed 1 minus sine y to the third. And that is going to be your second derivative, d squared y over dx squared. Now, you always want to look to see, so the final step here is to see if there's anything you can substitute for in the final answer from the original equation. And I probably could solve for cosine and make cosine, you could replace cosine here with x minus y plus 1, but I don't see the benefit to doing that. So this right here is your second derivative, cosine y over 1 minus sine y quantity cubed.